Why does the universe, our grand cosmic home, seem to play by two entirely different sets of rules? On a scale we can see and touch, everything appears orderly, predictable, and reassuringly solid. Planets follow their ancient, graceful paths around stars. A ball thrown into the air traces a perfect arc, its path sealed by gravity the moment it leaves your hand. A magnificent clockwork of cause and effect, gears turning in harmony. It's the world of classical mechanics, the physics that built our civilization and sent us toward the stars. But shrink your perspective. Journey down, 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 mountains, cities, a single grain of sand. Beyond cells past molecules into the realm of the atom. Here the rules dissolve into a bewildering carnival of strangeness. Particles become shimmering clouds of probability. They can exist in multiple places at once. They can be neither here nor there, but both until you look. This is quantum mechanics, as real as orbiting planets. Two frameworks, classical mechanics, quantum mechanics, twin pillars. Two languages describing one universe, sounding alien to each other. One promises certainty, a cosmos written in the stars. The other speaks of uncertainty, chance, and probability, observation shaping reality. How can both be true? How does solidity arise from probabilistic waves? From Newton's apple to Einstein's thought experiments to Bohr, we confront the limits of intuition and accept a stranger, more wonderful universe. We live on the seam between two realities, a bridge between clockwork and chaos. Explore both sides. Embrace the harmony of the large, the magic of the small. Let's begin in a world that feels like home. The world of classical mechanics. This is the physics of our everyday lives. A child spinning top the majestic sweep of galaxies. Its story is largely the story of one monumental genius, Sir Isaac Newton. In the 17th century, Newton gave us simple, elegant laws of motion and a universal law of gravitation. These laws were revolutionary. The same force that pulls an apple from a tree also holds the moon in orbit around Earth. The heavens and the earth were united under one set of rules. Newton's laws rest on determinism. If you know the position and momentum of every object and all the forces on them, you could predict the future with perfect accuracy. Imagine the universe as a colossal game of billiards. Exact starting position, exact speed, exact direction, and you could calculate every collision from break to pocket. In this view, the universe is a machine. Vast, intricate, and knowable, its future written in its present. These laws are the bedrock of technology. When engineers design a bridge, they calculate tension and compression, ensuring it withstands traffic and wind. When we launch a rocket to Mars, it's not guesswork. It's precise celestial calculation, plotting trajectories through the Sun, Earth, and Mars. Your phone's GPS uses the same principles, tracking you relative to satellites. This classical world feels certain. Objects have definite properties. A car has a specific location and speed. It cannot be in two places at once. Its path is continuous and smooth. Energy and momentum are conserved, transferred but never lost. This conservation brings order. It lets a pendulum swing and governs galactic collisions. For centuries, we believed this was the whole story. We thought we'd found the universe's operating manual. But we were only reading the first chapter. As the 19th century gave way to the 20th, cracks began to appear in the perfect facade of classical physics. Scientists studying phenomena like the light emitted by hot objects and the nature of the electron found that the old rules simply didn't work. The universe, it turned out, had a secret life. To explain these puzzling observations, a new theory was born, quantum mechanics, and with it, our understanding of reality was turned upside down. The solid, predictable world of Newton was replaced by a fuzzy, probabilistic landscape. One of the first bizarre discoveries was wave-particle duality. In the classical world, things are either particles, like a baseball, or waves, like a ripple in a pond. But in the quantum realm, entities like electrons and photons of light behave as both. Depending on how you measure it, an electron can act like a localized particle, or like a spread-out, undulating wave. It's not one or the other, it's both. This duality is a fundamental property of matter. Then, superposition. A quantum particle can exist in a combination of all possible states simultaneously. Imagine a coin spinning in the air. Classically, it will land heads or tails. A quantum coin can be both heads and tails at the same time. It's a ghostly blend until a measurement is made. Measurement forces the particle to choose. Wave function collapse. Your observation helps create the reality you see. And it gets even stranger. The uncertainty principle, from Werner Heisenberg, limits what we can know. You cannot know both position and momentum exactly. Measure position precisely, and momentum becomes uncertain, and vice versa. This is a built-in fuzziness of the universe. Finally, entanglement. Two entangled particles link so measuring one instantly influences the other, no matter the distance, across a room or across the galaxy. The journey into the quantum realm was not the work of a single mind like Newton's, but a collaborative, often contentious effort by a generation of brilliant physicists. They were explorers charting territory so strange it defied language and intuition. Max Planck took the first steps in 1900. While studying blackbody radiation, he proposed energy came in discrete packets, quanta. He thought it a trick, but he'd planted a revolutionary seed. A few years later, a young Albert Einstein took that seed he used light quanta, photons, to explain the photoelectric effect. That work earned him the Nobel Prize. The 1920s became the heroic age of quantum mechanics. A cohort of daring young thinkers built its mathematical and conceptual framework. Niels Bohr developed an atom model with quantized energy levels explaining why atoms emit light at specific frequencies. Louis de Broglie proposed that all matter, not just light, has a wave-like nature seen in electron diffraction patterns. Erwin Schrödinger formulated a wave equation describing how quantum states evolve over time, the quantum analog of Newton's laws. Werner Heisenberg developed matrix mechanics and introduced the uncertainty principle, linking observer and observed. These scientists, and others like Wolfgang Pauli-Max Born, wrestled with mathematics and deep philosophical implications. What did it mean for reality to be probabilistic? What was the role of the observer? The debates were legendary, most famously Einstein versus Bohr. Einstein: God does not play dice. He argued quantum mechanics was incomplete, pointing to hidden variables. Bohr replied, stop telling God what to do. Their debate forced physicists to confront the nature of reality, a conversation still ongoing. These architects of the impossible didn't just discover new rules, they gave us a new universe. While the principles of quantum mechanics might sound like abstract philosophy or science fiction, they are not confined to dusty blackboards, distant laboratories. The bizarre behavior of particles in the subatomic realm is the engine driving much of the technology that defines our modern world. You are experiencing the practical results of quantum mechanics right now. The device you are using to read this essay, a computer, a tablet, a smartphone, is a quantum machine. Its heart is a microchip filled with billions of transistors, semiconductor devices governed by the quantum behavior of electrons. Without our understanding of how electrons move through materials like silicon, transistors would be impossible. Classical physics predicts that electrons shouldn't be able to do what they do inside a chip. Quantum mechanics, specifically the theory of energy bands in solids, explains it perfectly. This understanding allows us to control the flow of electricity at an incredibly small scale, creating the binary language of ones and zeros that forms the basis of all digital information. Every time you save a file, stream a video, or send a message, you are relying on the predictable application of quantum weirdness. Look around you. The laser is another quintessential quantum invention. The word laser is an acronym for light amplification by stimulated emission of radiation. The key concept, stimulated emission, was first proposed by Einstein. One photon can trigger an atom to release a second identical photon. Contained in a mirrored cavity, this makes a cascade, a coherent focused beam. Lasers are everywhere. In barcode scanners at the grocery store, in Blu-ray players, in fiber optic cables that carry the internet across oceans, in delicate surgical procedures. The influence of quantum mechanics extends even into our hospitals. Magnetic resonance imaging, or MRI machines, produce detailed images of soft tissue through nuclear magnetic resonance. A powerful magnetic field aligns the quantum spin of protons in the water molecules of your body. A radio wave knocks them out of alignment, and the machine listens for the signals they emit as they return. By analyzing these signals, a computer constructs a detailed three-dimensional map of your internal anatomy, all without any harmful radiation. From computing to communication to medicine, the quantum world is not a distant, strange land. It's the invisible foundation of our 21st century lives. So we have these two magnificent theories, classical mechanics, quantum mechanics. Both are incredibly successful within their own domains. But how do they stack up side by side? The most obvious difference is scale. If the universe is fundamentally quantum, built on a foundation of uncertainty and probability, Then where does the solid, predictable classical world come from? The answer lies in a crucial concept known as the Correspondence Principle, first articulated by Niels Bohr. This principle states that the predictions of quantum mechanics must agree with the predictions of classical mechanics in the limit of large systems. As you scale up from the atomic to the everyday, the weirdness of quantum mechanics should fade away, leaving the familiar certainty of Newton's laws. This transition happens through a process called quantum decoherence. A quantum object, like a single electron, can maintain its strange superposition state as long as it is perfectly isolated from its environment. But in the real world, perfect isolation is impossible. A macroscopic object, a dust mote, a baseball U, is constantly interacting with its surroundings. Trillions upon trillions of air molecules, photons of light, and cosmic rays are bombarding it every microsecond. Each of these tiny interactions acts as a measurement, observing the object's position and forcing its quantum wave function to collapse. And what emerges is a single loud classical shout.